For the introduction, to understand heat conduction, in the realm of heat conduction, eigenvalues emerge as crucial elements, playing a vital role in unraveling the intricacies of temperature distribution. As we explore this topic, keep in mind the following key points. Heat conduction context. Eigenvalues are crucial in the analysis of heat conduction. They play a vital role in solving partial differential equation PDEs governing temperature distribution within materials. Next, symbols and definition. T represents the temperature distribution. NABIL square is the Laplacian operator. The Laplace equation, the fundamental PDE for steady state heat conduction is the Laplace equation. NABIL square T equal to 0. Second order PDE. The Laplace equation is a second order PDE. Solutions to this equation often involve the use of eigenvalues and eigenfunctions.
Now we move on to theoretical background. This is the equation where the general equation is being created, and the numbers below it are the equations where it can be used on different situations. So for the first equation, the equation can be written as shown, and since both depend on different variables, they must be constant where the constant v is equal to 1 over r. And for the second equation, the eigenvalues h equal to 0 are real positive discrete lumps not bounded from above. The differential operators of the temperature problem and the Schrödinger wave problem are symmetrical, ensuring the eigenvalue spectrum is real. And the equation can be written as shown. And number 3, since material functions are always positive, another product can be defined. The product equation is written as shown. For fourth, the complete temperature field within V as solution for general HXT with zero deletion and Newman boundary conditions can be written as the equation shown. Then if the position independent inverse eigenvalues are the time constants of the system and only depends on the geometry of the setup, its material parameters and its boundary conditions. Based on these conditional things, the equation can be written as shown. And for fifth, the sum under the integral can be identified with the time derivative of the thermal independence for the position x called z position xt minus r. Z position xt minus r is the temperature rise at position x for constant dissipated power P of unit strength starting as T equal to 0. Unit step response can be written as the equation shown. Last but not least, the sixth. The eigenvalues and the eigenfunctions will be calculated for multi-layer structures in the next section. However, the measured or simulated Z position T curve for a specific location X can be represented with very good accuracy by some of previous equation with only m equal to 6 to at most 16 effective pairs. The pair can be chosen to be the same for all x as the equation showed.
Results and discussion. So this is a heat conduction material. The thermal behavior of materials can be crucially understood from the results of eigenvalue analysis in heat conduction. The thermal diffusivities or eigenvalues show how rapidly or slowly heat moves through a substance. The accompanying eigenvectors provide insight into how various heat conduction modes contribute to the overall temperature profile by describing the temperature spatial distribution. So there are two heat conduction contexts. The first one is eigenvalues are crucial in the analysis of heat conduction. They also play a vital role in solving partial differential equation (PDE) governing temperature distribution within materials. Another useful application of eigenvalue methods is the solution of transient heat conduction issues. Engineers are able to forecast the evolution of temperature distributions over time by taking into account the time-dependent solutions of the eigenvalue issues. Understanding transient heat conduction is essential for applications like electronic device thermal management as it prevents overheating and guarantees component dependability. High thermal diffusivities suggest efficient heat conduction while lower values indicate slower heat transfer. Eigenvalues analysis is particularly useful in scenarios where the material properties vary spatially or temporally, allowing for a more nuanced understanding of heat conduction. So this is the IGBT multi-chip module. It shows the top side of the heated IGBT module in stationary state. It took several hours to calculate the 446,745 eigenfunction and values.
As we finish talking about eigenvalues in heat conduction, let's sum it up. We learned how they help us understand temperature change, where they are used in the real world, and how they balance accuracy and efficiency. Now let's look at four main points. First, the dynamic understand of time-dependent temperature distribution in heat conduction is facilitated through the use of eigenvalues. Eigenvalues contribute to a comprehensive comprehension of how temperature evolves over time within a given material or structure. Next, eigenvalues demonstrate practical applicability in real-world scenarios, particularly within a multi-layer structure such as AC packages and power electronic modules. This application highlights their relevance and effectiveness in addressing complex challenges encountered in practical engineering context. The third point, the challenges associated with computational demands are effectively addressed by leveraging eigenvalues, which optimize numerical effort. This strategic use of eigenvalues streamlines the computation process, ensuring efficiency in handling complex calculations related to heat conduction analysis. And the last one, achieving a delicate equilibrium between modeling precision and computational efficiency is essential, particularly in scenarios with high resolution requirements. In summary, eigenvalues present a practical and efficient methodology for the analysis and prediction of time-dependent conduction phenomena across diverse engineering applications. Our exploration of conduction is an eigenvalues problem. We draw insights from the work of Gerstenmaier and Washuka 2002. Their contribution and encapsulated in the publication titled Heat Conduction as Eigenvalue Problem, part of the lecture notes in Computational Science and Engineering series.